All right, so today I want to talk about something really cool. I want to talk about zombie processes. Now, if you're on like Linux, this also affects like, Mac OS or like FreeBSD or whatever. You've probably encountered zombie processes. Maybe you ran like PSEF and you see something is defunct. And you're like, okay, well, what exactly is that? What is a zombie process? Maybe you try to kill it. Maybe you send it a kill signal or a kill-9 and you're like, okay, well, kill didn't return an error, but the process is still running, right? Or at least the process still shows up in PS. Is it running? I can see it. It has a PID. I can send it a signal, but nothing seems to happen. What's going on? We're going to demystify that today because, yeah, I think it'll be a lot of fun. All right, so normally I would jump right into code, but for this one, I think I want to talk about it a little bit first, then we'll jump into the code, okay? Because we're going to make our own zombie processes. It's surprisingly easy to make a zombie process. All you have to do is be a negligent parent. I joke, but that's actually how it's done. So if you're sitting here and you're wondering, like, what exactly is a zombie process? I don't really understand it. Is it running? Is it not running? It's not running, but it has not been cleaned up yet. So it is in that intermediate state. I'm going to make an analogy real quick, okay? Imagine you're playing a video game. You're playing maybe some like first-person shooter game, whatever. Even you're playing like GoldenEye 007 for the N64. Goated game. I love it. When you shoot at one of the guards and you eventually pass them away and they're laying on the ground and they are unalived. I'm kidding. I'm not going to talk like that for this video. So in that game, you shoot a guard, you kill them, they're laying on the ground, right? Their body's there. They're dead. They're not running around. They might have an AI in the game that tells them, go check this, go check here, go run here. That AI only runs if alive. So if it's not alive, it's just laying on the ground, right? So there's a body on the ground. In terms of the computer program running behind the scenes, there's a body there. There's like maybe some physics on the body. There is a guard there. The guard isn't doing anything, but it's there. It's taking up space until it disappears from the playfield. Eventually, they just disappear. Once they disappear, then it's gone. Then the memory can be cleaned up. So much in the same way, a process exists. It has a PID, a process identifier, and it does something. It has work to be done. The kernel schedules it to do that work in the CPU. When it dies, it needs something to call wait on it. Wait is a syscall. It's actually a family of syscall. I think there's like wait ID, wait PID, wait TID. I don't know. But basically it needs something to call wait on it. It needs the parent to call wait on it. So when a child dies, the parent process actually receives a signal. It receives a sig child, and it's up to the parent process to call wait on the child. Wait informs the operating system like, hey, let's actually get some accounting info from this. Like, hey, what was your return code? How were you killed? Were you killed by a signal? Did you stop running of your own volition? Like, I need to get some of that accounting info. Until I get that, it just sits there. It has a process ID, but it's never being scheduled, so there's nothing to run. Because as a process ID, you can send it signals, but it's never being scheduled. None of those signals are ever going to run. The process is dead. So that's what it is. A zombie process is a process that exists in that state for an extended period of time. So the parent never calls wait. That's what I made. That's the joke I made when it said it was a negligent parent. So if it's helpful, you could think of it like a memory leak in a program, okay? You have a program and it allocates memory, and when it's done with that memory, it's supposed to free that memory. If it never frees that memory, it's still taking up space, whether the program's using it or not. You would say the program's being bad if it's not freeing the memory it's done using. The same way that a parent is being bad if it's not calling wait on the children that have died. Now, when you see a zombie process, it's not indicative of a problem with the process itself. It's indicative of a problem with the parent. The parent is doing something wrong. The parent's stuck doing something else. It's just not watching over the child processes. So that's probably where the bug lies. If there is a problem, it's because of a life cycle in the parent, not in the child. The child's already dead. There's nothing else it can do. It's just signal to the parent like, hey, clean my body up. And the parent's like, nah, I got better things to do. If you kill the parent process, then by traditional Unix life cycle of processes, maybe some operating systems do it differently, but I know in a typical Unix environment, what will happen is the children will be rehomed. They will be reparented. Now, they don't get parented to like the grandfather. They don't go up the chain. They go up the chain. Well, they don't go up the chain by one level. They go up the chain as far as they can go. Typically, that would be like the init process or whatever your PID1 is or whatever that main process is. So that process that starts in your system, it's responsible for calling wait on all of its children. So when there's a zombie process, if the parent dies, that zombie gets rehomed to init, the top process, and that calls wait on it. So the zombies will eventually get cleaned up and reaped. Unless you have like an init process that is not acting the way it should be, but then you have bigger problems if that's what's going on. So that was a lot of yapping. Normally I don't yap that much. Let's dive into the code because I think that's going to be fun and probably clear up some things. So here we go. We're on Linux. We are on Void Linux, and we are going to make some zombie processes. There are a couple different ways to do it. I figure using C is the easiest way to do it. So let's go ahead and do that. Let's make zombie.c. This will be a simple program. I already started typing a bash shebang. That's so funny. This will be a simple program to make a zombie process in C. So let's return 0. Now we have the world's simplest C program that just returns success. The first thing we need to do is we need to call fork. Fork is how a process will split into two. This is how processes are born. There will be two copies of the exact same process running, but this is how they're born. So before we even do that, let's go ahead and man to fork. Fork is a syscall, so it's in section 2 of the man pages. Pull this up. We're going to need the Unix standard header, and fork returns a PID-T. So that's very important. What does fork actually return? Scroll down a little bit, return value. On success, the PID of the child is returned in the parent, and 0 is returned to the child. On failure, -1 is returned to the parent and no child process is created. Perfect. So it's -1, 0, or a positive integer if we are in the parent. Okay, cool. So knowing that information, we can do a couple things here. We can pull that include in for the Unix standard header. We can do a PID-T of PID equals fork. And there we go. Now we've forked the process, and we could do something really simple here. We could just printf hello world with a new line. Now we will need standard IO because we're using printf. So standard IO.h. There we go. Let's cc. I'll pull up the source code. Bat make zombie. cc make zombie into make zombie. There we go. Now we have a make zombie program. If we run this, what do you think's going to happen? It prints hello world twice. The parent printed hello world and the child printed hello world. This is weird if you've never seen it before. So this function fork is a very special function. It enters once and returns twice. So the parent printed hello world and the child printed hello world. Which order? Depends on the scheduler. Typically it might be the same, but it depends on the scheduler. You can't really rely on the ordering here because they are two completely separate different processes now. We can prove that. Let's go ahead. First thing we should do is check for the error. Do you remember what the error was? -1. If we hit here, then we failed to fork. We can do better error handling. We could actually use like P error or something, but let's just do this. If we get here, we failed to fork, we should just return 1, and then we don't go any further. But now if we're here, if the PID is equal to 0, then we are in the child. In child program. Otherwise, then we know that the PID is greater than 0. We are in the parent. There we go. So let's go ahead and close that. Let's copy and paste this. So we'll say child says hello world and parent says hello world. There's nothing zombie about this going on yet, okay? We have a parent process, a child process, and they both immediately exit as quickly as they can after printing hello. So let's go back, let's pull up that source code, let's compile the program, and let's rerun make zombie. So the parent says hello world, the child says hello world. That's how we can differentiate in code. This branch is for the child, this branch is for the parent, but they both exit. See? Super simple. Now what do we need to do in order to be bad? In order to make a zombie process, we need a child that dies and a parent that is negligent. So the child has to die, the parent has to live, because if the parent dies, then the child will get owned by a nit and it will be reaped. We need a parent that lives forever but never calls wait. So the child just needs to die. We'll return a success right there. Perfect. There you go. So child, let's just say dying, ... Now, if we are in the parent, we can say parent creating zombie process %d, and that is the PID of the child that we have. So we are going to create a zombie process. In order to do that, we just need to do nothing. So we need an infinite while loop that just calls pause. Now, pause is really cool if you've never seen it before. You run pause. Do we already pull in the Unix standard header? I think we did. Pause is super simple. Causes the calling process or thread to sleep until a signal is delivered that either terminates the process or causes the invocation of signal catching function. So pause does nothing, and it does nothing very effectively. So we just put pause in an infinite while loop. Never exit. LOL. There you go. So that's it. This is it. This is all you need to make a zombie process. So let's go ahead and show that source code. There's a lot here. Oh, I brought it to a pager. That's super annoying. So yeah, all we're doing is if we're in the child, we just die. Simple as that. If we're in the parent, we just pause forever. So the parent is negligent, the child dies. Let's go ahead and recompile that and run make zombie. So there we go. The child's dead. We have a new zombie process of 3417. What I'm going to do is I'm going to pull up a tmux here. And we're going to pull up multiple panes here. So there we go up here. Let's make a zombie process. There we go. So now we have a zombie process of 3609. There we go. So now if we ps, ef, and grep for defunct, you can see, look at this. We have our defunct process. We have our zombie process, 3609. That makes perfect sense. We can also, I think, ps tree, what does ps tree take? The PID itself? Oh, that's not that helpful. -A, puts it in parentheses. -P for PID. Let's pull up the man page because I don't remember. How do you get to show everything? Oh, -S shows parents. Okay. So I don't know what T did. There you go. This looks good. So my init system, because I'm on Void Linux, is run it. Run it as PID1, which owns tmux, which owns bash, which owns make zombie 3608. That's the parent that's running. And then make zombie the child 3609. 3609 is not alive. It's not running, but it still has a PID. It still has accounting info. It still has stuff waiting to be processed. If I ls proc on 3609, you can see that we get a lot of errors. We get some failures to read this, but it still has a proc file structure. So it's still there. It's just not running. Nothing's happening with that process. In fact, if I were to kill 3609, you can see that, well, it works. I can send it a kill signal. I can keep sending it a kill signal. It doesn't do anything. Nothing's processing the signals. Kill -9. It should kill it right away, right? Nothing's processing the signals. If I kill the parent, which I think we said was what, 3608? Let's go ahead and verify that before we do anything drastic here. 3608 is the parent. If I kill the parent, I could also just go up in the terminal and control C it, but let's go ahead and kill it this way. 3608. Then we get the terminated up top. The parent is gone. Is that child still around? Well, if we PS there, that process is not found. If we do the PS -EF for defunct, it's not there anymore. So by killing the parent, the child was rehomed to a NIT, and then a NIT reclaimed it or called wait on it or reaped it. That's how you would describe that. So yeah, in our simple example, it's really not that big of a deal. We just create a simple, that's not what I want to look at. We just created a simple zombie process. That's super great. But we could call fork 100 times or 1,000 times, or maybe you're in like a mission critical server. You're in some sort of web server that has a bug and it's forking children to handle new requests and it's never reaping them. So then you have one defunct process, and then 10 minutes later you have 2, and then 10 minutes later you have 4, and then 10 minutes later you have 8, and then 10 minutes later you have 16. You see how this can become a problem? The problem never lies in the child itself. The problem always lies in the parent. It's indicative of a problem. A zombie process is not a problem in and of itself. It's indicative of a greater problem with the process and lifecycle management in the parent. That's where you need to look. So when you have a zombie process and you're over here like, oh no, my zombie process is 3950. Uh-oh, I need to kill that. I need to kill that. I need to do this. Kill it all you want. It's not going to do anything. Killing sends a signal to your operating system. Your kernel turns on a flag in the process structure, and that flag gets processed when that process is scheduled. This process never gets scheduled. Nothing handles these flags. These flags are ignored. The signals are doing nothing. You got to deal with the parent. So PS3, was it SAT 3950? There you go. Yeah, your issue is going to be here. I don't know why I keep putting T in there. I don't think it's right. SAP? There you go. Our issue is here. Our issue is 3949. So we'd have to actually kill 3949. If you're on a mission critical system, don't just take down the parent of a zombie process without understanding what's going on. Obviously, make sure that's safe to do. In our example, it's a simple contrived example, but yeah, so yeah, hopefully this demystified zombie process for you. I'll put all this code online. I'll have it like linked in the description and stuff. So yeah, hopefully this was educational. Hopefully you enjoyed it. And of course, I want to leave you guys with this. Obviously, you should subscribe to the channel. I want 100,000 subscribers, but I do have 100 active members on Patreon. Check that out. Thank you to all my patrons over at Patreon. Check it out. You guys are awesome. If you want your name at the end of the video, go ahead and sign up for my Patreon. And yeah, link will be in the description, or you can just go to this link right down here. Of course, it's not a video, so you can't easily click it. So yeah, there you go. Thank you everyone for your support. Hopefully you guys enjoyed this video. And yeah, that's all I got for you. See ya.